In this video, I will be using one of my favorite analogies to explain various concepts of functions, which is the blender analogy. Now, I use this when I introduce functions and I teach different concepts of functions for my students. And typically, I start off by introducing the input, function, and output scheme with functions. So the input, of course, is your fruits, and you use a blender, which is the function, which the function is to rotate its blades at a really rapid rate and then cut off chunks of the fruits and eventually convert it into a pulp of the juice that we get as an output, right? So that's how I introduce the input, function, and output, right? So now mathematically what this would look like is input would be your x, right? And then the function is any letter, usually f, which is what we start off with. And then your output is, you have your input x and you apply f to it of x. That's how you would read this. F of x is your output. All right, so here's another really nice tool from Mathigon. I think it's relatively new, which is function machines. Another really nice scheme, which is, you can see input. The function here that I've chosen is x plus 1, which means x, remember that's the input that we saw earlier. And this, what it does is basically add 1, which is the operation or the transformation, and then gives you an output. So I really like to use this as an interactive method to showcase the concept. You insert 3, you get 4. Maybe you take 4 again and use that as an input, and then you get 5. You could use maybe negative numbers. I'll use minus 10 from here, get that, and let's see what happens. Of course, you add 1 and then you get minus 9. You could use fractions as well, or decimals. Let's use 4.5. That works the same. Take that, and that goes in your input, and again add 1, right? I could do another function machine. Let me change the color there to purple, and I'm going to modify my function. So I'm going to change what my function's doing. Okay, so I'm going to do 2 times x. Okay, so multiply by 2, and maybe I'll use one of my outputs from here. 5 multiplied by 2, I'll give you an output of 10. And if you had, for example, a negative number, you multiply by 2. Yeah, so I could label these functions as could be, this could be f, this could be g, right? There are 2 different functions, so I'm using 2 different letters. So here's we saw what the blender analogy looked like. That contained input, function, and output. Now here's a scheme, which again is used to depict what a function does. All right, so we just looked at how function machines can be used to insert various inputs, and based on the operation within that function, you'd get a transformed input, which is the output. Okay, now can we use any input and get a meaningful output? Well, for that, I'm going to use the analogy of the blender again. So what if I use nuts, stainless steel nuts or bolts as the input for my blender? Well, we know that that's not going to end well, right? It's going to cause the blender to fail or break down, or something bad's going to happen. We know that. And why? Why did that happen? Because, well, the characteristics of the blender itself, the material it's made from, the type of blades, the strength of the blades, things like that. I mean, it's not going to handle that input, which is nuts, very well. It's going to fail. So it's the inherent property of the blender itself that caused it to fail. So in that case, we want to avoid inputs like that, right? So how do we communicate that to the user or someone who's going to use the function? Well, that's where we need a domain to tell us what we can use. So the domain, in this case, what the manufacturing company will do perhaps is tell you, okay, you could use fruits, you could use vegetables, you could use seeds of certain types to convert that into powder. Even beans, like coffee beans, things like that might be listed there. So you explicitly telling the user to use these stuff. And that's what the domain is all about. That's true with mathematical functions as well. So let's take this example. F of x equals the square root of x. Now, for those who know about the square root function, you know that's a bad idea to try and obtain the square root of a negative number. And that's an inherent property of the square root, which comes from the fact that you can't multiply two identical numbers, to get a negative number. So because of that property, this function is going to fail if you try to use a negative number for x. If you try to obtain the square root of a negative number, that's not going to give you a meaningful real output. What's the domain of this function in that case? Well, can we list down every single number that we could use? 0, 1, 2, 3, 4, 5, and even the decimals, all of that? Well, that's an infinitely long list. So we're not going to do that in this case. Well, that's sometimes used in math functions, certain math functions where the number of inputs is not that large. Well, so that you could use an explicitly tell the user what numbers or what values you could use. But in this case, it's simple. You could use an inequality, for example. Your domain could be, it could say x greater than or equal to 0. Remember, you could include 0 because the square root of 0 is 0. Or you could even use what we call a number line to show this. That, and then you would indicate 0, and then you would shade a circle like that to show that it's inclusive of 0, and then mark that, showing you could use any number up to positive infinity. And that's how you would show your domain in math functions. Sometimes it's not just the properties of the function that determine what we need to leave out from the input. It could be the application in which the function is applied. Let's take this scenario, for example. You take water and you use that as the input to our blender, right? Is this going to fail? Well, not really. The blender can handle this. It's not going to break down like it did with the nuts and bolts that we used last time. But as an output, we are going to get back water after it takes a little bit of spin, right? So why don't we include water as part of the domain? Shouldn't it be in that list that we created, explicitly listing fruits, vegetables? Shouldn't water be part of it? Well, not really, and that's because water does not serve the intended purpose in which the blender is being used. So it's not part of the application. It does not make sense to use water with this function. So we are going to leave that out from the domain. And that's exactly how mathematical functions work as well. Sometimes you need to think about what the application is. Let's take this example. F of x equals 3x plus 20. Let's say this is a function that's being applied by a taxi service to charge its customers. Now what happens here is x, the input, is your distance of the ride, let's say. And f of x, obviously, is the charge or the fare that the customer needs to pay. Now, if you look closely, it's a linear equation. You could use any input and the function is not going to fail. It'll give you an output. You could use negative numbers, you could use fractions, positive numbers, anything, right? Let's just say at the distance x, our input over here, we use minus 10. Could you find out what happens then? Well, you're going to get an output, but that output, f of minus 10, is going to be minus 10. What does this mean in the context in which it's being used? What that means is, if for some reason an input of minus 10 is applied, the taxi service has to pay the customer instead of the other way around. So that's a failure in terms of the application. So here we need to make sure that the domain leaves out negative numbers. So we want to use x greater than or equal to 0, right? So that's where the application dictated terms and created a restriction on the inputs that we can use. Another example that I can use is this over here, a production line, where P of X is the profit that a production company makes after it ships X number of items. Take some time to think about what the domain of this function should be. If you look closely enough, this is also a polynomial. Now, all polynomials can accept any real number and will give you a real output. That's a property of any polynomial. So what do you think? You may have already thought that we can't use negative for x. That's because the number of units produced can't be negative. It has to be a positive value. But did you think that x also has to be an integer? It cannot be a fraction. That's because it's units of boxes, these boxes. So it has to be a number, an integer, 1, 2, 3, something like that. Can't be fractions. That has to be x. Now, how do we do this? How do we list the domain in that case? Well, we can't use an inequality. If you try to do so, I mean, we can't leave out the fractions. So that's where we have this set called z, which are all the integers, the set of integers. But we know that we can't use negative integers, so we have the set of positive integers. So these were two examples when the application in which the function is applied dictates what your domain has to be. We can classify functions into various groups based on the mapping of their inputs to the outputs, which is basically the relationship between the set of inputs and the set of outputs of that particular function. Let's go back to our favorite analogy of the blender once again and see how things work. So on the left hand side, I've got a set of inputs that I'm going to use on my blender, which is the function over here, and then I've got my set of outputs right here. Right. Let's take our first input, which is a watermelon. Right. What happens if I pass it through a blender? Well, it's pretty obvious. You're gonna get watermelon juice. That's the only thing that could happen. You put watermelon in, you know for certain you're gonna get one input, one and only output, sorry, which is watermelon juice. So if you do that for kiwi, you're gonna get kiwi juice, right? So what we see here is a one-to-one mapping or a one-to-one relationship where you have a particular input, one input, and maps to one unique output, right? Now, let's see something like this. Okay, what I've got here is a bunch of fruits. I've got lime, pineapple, oranges, kiwi, a collection of fruits. And I'm going to put this all at once. So this bunch of fruits is going to be an input, right? What happens now? Well, that goes on to become what I call the mixed fruit drink. Okay, so it's given us an output, which is a mixed fruit drink. Then I'm going to use another different input. So if you look closely, it's not the same input as earlier. Yes, it's a bunch of fruits, but it's different. You got dragon fruit, you got mango, and a bunch of other fruits. What will happen here? Again, if you pass it on the blender, and for a moment, if we decide to overlook the intricacies like the composition, this too is going to be a mixed fruit drink at the end, right? You could classify it as a mixed fruit drink. So what has happened here? You've got one input, two inputs, or you could have many other combinations and several other inputs, many inputs that map on to this one output, which is a mixed fruit drink. So that sort of relation is what we call a many-to-one relationship. So you can have both of these, one-to-one, many-to-one relationship in functions. There are even more permutations like one-to-many relationship, but that's not classified as a function. right? If you see something like that, where it's a one input mapping onto two outputs, which really in this sort of a context with a blender does not make sense at all, right? That sort of thing does not classify as a function. Now we are diving into the more interesting concepts in functions. Let's say we want to use our blender that we've been using all this time to make some carrot juice. How do we do it? Well, one option is put a whole piece of carrots into it and blend it off and see whether we get juice. Well, that's not going to work as well because blenders are not that good at handling big hard chunks of carrots. What do we do instead? The typical process is first you break it down into tinier parts using a grater of some sort, and then once you get that, you pass it onto a blender. So you do two things. One, you start with your input, which is your carrots, whole carrots, pass it to a function. That's the grater. I'll call that G for now. And then you pass it on to another function. You do another set of operations onto it. I'll call that F. And then ultimately you get your juice, right? Now, could we combine them and get the collective machine? Could we have a machine that does both of them at once, where I just have to insert my input and then voila, I get my carrot juice in one step? Well, that's what we call in real life the extractor. The extractor does exactly that. It does both these functions in a single machine. So this is a single machine that does both G and F. And so similarly, mathematical functions also can be composed. We can get composite behaviors from functions as well. All right, now let's use function machines to understand how composite functions work. Let's see how the collective behavior can be understood using the function machines that we just built previously. So the first function here is x plus 1, which adds 1 to the input, and the next one multiplies it by 2. So what I'm going to do is first carry out the blue function and then the next one, so in series. And so if we use an input, I'm going to use 1 here. So it should add 1 to 1 first, and then whatever result I get here, it's going to be multiplied by 2, which is going to be my final output. So let's see what happens. There you go, and you end up with 4. Okay, so that's what the two functions do together, right? Now the goal has to be, how do I replace both of these functions in a single function? For that, I need to understand what net effect does this have on a given input x. If I know that, I could replace it with a single function. Okay, so let's see what happens to x. I'm going to use an arbitrary value x, and then okay, so the output is going to be x plus 1 because it's just going to add 1. Then it's going to multiply this by 2 because that's what the second function does. So at the end, I'm going to get this. So in effect, what has happened here is, let me use this. If we consider both these functions like that, and if that's a single machine, it has taken x as an input and given me 2 times x plus 1. So I'm going to forget whatever's inside that. I'm going to consider it as a black box, which is what I'm going to replace with my new machine. So what does that have to be? This machine has to take x. Well, it gives me 2 times x plus 1. That's what we saw from the net effect. So if this took x, it will give me 2 times x plus 1 because that's the function. I'll change the color of that to red. There we go. Let's test it out. Let's see if this works. I'm going to clear things a little bit. Let's clear this. Let's clear that. Okay, so let's use 5 as our test. I'm going to use 5 as an input. Let's see what we get. 12. Okay, so this single machine, the composite function, should pretty much do the same thing. And yes, it does. We get 12 as an output. We could try doing add 12 again. Let's see what that works. Get 26. Let me put 12 back in again. 26. So what this means is I've found an equivalent machine, a single machine that does the job of these two functions, which is adding 1 and then multiplying it by 2. So this is the composite function. How important is the order of composition? Does it make any difference to the net effect on the input if you change the order of operations? Let's take the same example as earlier. You've got big chunks of carrots, and then you grate it, break it down into smaller ones, and then you pass it on to the blender, and of course you get carrot juice as expected. But what if we decide to reverse the order? Now, if you look at 1 and 2, we are still performing the same set of operations. But what would happen? You'll have, first it'll go to the blender won't do a really good job, it'll perhaps break it into somewhat large chunks, and then you could use the grater and then break it down into fine gratings, perhaps at best. But you're definitely not going to get your carrot juice. That's impossible. So what you want to see here is that when you switch the order of operations, the output will not necessarily be the same. It could have a dramatic difference. Now, sometimes in unique circumstances, when there are special functions being composed, there is a chance that when you switch the order, it could still have the same output. But that's only under special circumstances, under special functions. But unless that, you should expect to see a change when you change the order of the operations. Now, this is true even for mathematical functions. Here's the same composition that we saw earlier. We've got x plus 1 followed by 2 times x. What I'm going to demonstrate here is what happens if we change the order of the composition. Is this going to be an equivalent composition, or is it going to change things? Let's find out. So I'm going to use the same input on both compositions. And let's see what we get as our output. Well, the first composition gave us 12 and the second gave us something different, 11. So why did that happen? Well, like we discussed earlier with the blender example, changing the order of composition creates a different net effect altogether. So the net effect from the first composition is different to the net effect from the second. You can actually verify this by doing what we did earlier. Find out what the composite function of this is and match it up with the composite function of the second composition, and you'll see that those expressions will be different altogether. So this doesn't happen all the time. It's not always going to be different. Okay, there are some special types of functions, unique operations, that when you compose them together, despite changing the order, it's still going to give you identical outputs. I'll show you an example like that. All right, here's a new composition. I've got x divided by 5 as my first function. Then I've got 4 multiplied by x. I'm going to do the same thing we did earlier. I'm going to change the order. Remember, the only difference in the compositions is the order of operations. All the functions are identical. So what will happen here? What do you think? Well, we could try 2 inputs. Well, we've got the same output despite changing the order. Now, could be coincidence, so I'm going to use a different input and see if that works as well. Could try a negative number and see that in fact the outputs will still remain the same. Alright, so this has to do with the properties of the functions that I've chosen to compose. So dividing by 5 and then multiplying by 4 is in fact identical to multiplying by 4 and dividing by 5. Right? So it doesn't matter if we change the order. Now, these are not the only types of functions. There are some other relationships between functions that, when composed, will have the same net effect. So the net effect from this one and the net effect from the second composition, which is just swapping the order of the function. Now, this could be two or more functions, right? Composition. If the net effect, overall effect of the functions are same, which can happen in unique circumstances, then no matter what the order is, you get the same output. I encourage you to find out what the net effect is, basically what the composite functions are for these, and if you simplify them out, you should see that they indeed match. They are actually equivalent composite functions. Another core concept of functions is the inverse of functions. To understand this, let's take the usual scheme of functions where you have an input x, you perform a transformation with f, which is just a series of operations, mathematical operations, and then you get your output, right? And let's assume that the series of operations are a, b, and c. Now, a, b, and c are basically the transformation that x undergoes in that particular order. So what it means is you have x, you do some operation a, could be multiplied by 2, divide by 2, obtain the square root, could be anything, right? Any mathematical operation. And then what you get from that, you do b onto it, which again could be any mathematical operation. And then you do c, and you get your output. Okay, let's see you're doing 3 operations. Okay, so the inverse function, the role of the inverse function is to do exactly the opposite, the inverse, to undo what was done to y, right? So that looks like this, where f minus 1 is the notation for inverse, minus 1 in superscript. Now what this does is basically, if you have y, the output of the function, since it undoes everything, it undoes c, b, and a, and then gives you back your input. And you can see why we call it the inverse, right? You can restore your input. Okay, so how does it do this? Well, to understand this, I like this analogy. So let's assume this is what f did. The function f added layers of shirts onto the body, right? And you want to undo this. How do you do it? First, of course, you have to start off by removing the last layer of clothing that you added. That's why we call it last in, first out. It's a very popular concept in mathematics and programming. Now, how do we do this? Well, we got to start by undoing this. So you have to undo c, then undo b, and then undo a, in that order. So that order of undoing is important, right? Whatever you did last should be undone first, right? That's how it works. You can also think of it as a stack that you add on. Let's say a, b, and c was transformations in that particular order that you did to x. If you want to restore back x, you have to get rid of c, and then b, and then a. That's the holistic view of how inverse functions work. Let's take a look at how this works with mathematical functions. Let's use function machines to understand how inverse functions work. I've got the same setup as earlier, and let's first use a sample input and see what we get. We got 12. So we used 5 as an input and we got 12. Now the purpose of an inverse function is to actually restore what we've done, right? So if we have an output, I should be able to restore my input from that output. So to do that, we have to undo what we've done. And remember, we are following the approach of last in, first out. So I have to start by undoing what I did last, which is 2 times x. How do I invert that? Well, multiplication, the inverse of that is division. So I'm going to divide by 2. Then I'm going to try and undo the other operation. and that's an addition, so I am going to do subtract 1. Now this should pretty much be the inverse. So if I input 12, it should restore and give me my initial input, and it does exactly that. Now I made emphasis on the fact that we have to undo in a certain order, last in first out, the analogy of the clothing layers, removing from the last layer onwards and backwards. What if we don't do that? So if I switch the order, remember I'm still doing the undo operations. I'm doing x minus 1, which is the inverse of this, and x divided by 2, the inverse of that, but just the difference is that I've switched the order. Now let's try using 12 as our input once again, and let's see if that will give me my original input. Well, it doesn't, right? So it does not work like that. So if you want the inverse, remember the stacking method, the stacking approach. You start by removing the last operation that you performed on that particular input and work your way backwards to restore the input. So if this is the function f, what we have here is the inverse of that function. Now what I have here is the composition of the two functions. Now this sums up or gives me the overall effect, or the composite function that we obtained earlier as well when we were discussing composite functions, which is 2 times x plus 1, which is, this basically replaces, this is a single machine that replaces the two functions above. Now if you remember, this was the inverse that we just obtained a while ago, and here's the composite of that. So I'm going to replace that with a single machine because it's easier to work with. Now what I want to try and do is try and understand what will happen if we decide to compose this. What if we try and bring them together as a single machine? What do you think? What sort of composite function would these two make together? Now remember, these are not just ordinary functions. This is f, and this is the inverse of that. Now what happens if we try and compose two functions that are the inverse of each other, right? Let's use some inputs to understand it. I'm going to use 1 to start off. Okay, we still end up with 1. Okay, maybe it's a coincidence. Let's use 2, and let's see what we end up with. Well, we get back our original input. So it seems like the net effect is that nothing is happening to the input, right? Overall, once it passes through f inverse. Now if you really think about it, that's pretty obvious, isn't it? That's the role of the inverse. So whatever f does, I'm going to indicate that using an arrow. F inverse is going to do the exact opposite. So if it's like moving 2 steps up and then 2 steps down. Well, you haven't gone anywhere. If you started with x, you would still end up with x, even though whatever happens in the intermediate steps, it eventually cancels off. So that's why I mentioned earlier that inverse functions are special, right? If that's a special kind of relationship when you compose them. So why is it special? Because if I decide to change the order, right? I change the order. Now if you remember, changing the order could change the net effect unless it's a special type of function or special types of relationship within the functions that are composed. That's what I told you. Now here's a special relationship. What will happen here is that the net effect doesn't change. We still end up with the input, right? Nothing really changes. So the net effect remains the same despite changing the order when the functions that are being composed are inverse of each other, right? So eventually you're not doing any work. An interesting exercise that I would encourage you to try as a learning process would be to try and find the net effect of this. What's the composite function of this when you have f and f inverse? And come up with your own function and come up with the inverse and see what the composite function is. And you'll find out, if you simplify it to its simplest form, it will just be x. What that means is, if you have an input x, the function just keeps it as itself. The net effect, remember, both of them collectively as a black box, remember, it does not do anything to the input and gives you back x. So with any inverse function, the composite function is this, which means no manipulation, no operations done on x. So that's something interesting you can derive on your own. We have now looked at some of the most important concepts in functions, and I hope you found the analogies that we used with the blender and some of the illustrations with function machines on Mathagon useful to understand or get a more broader view of what functions are. And that was the main purpose of this video, really. So I encourage you to use Mathagon and its function machines on your own to experiment things, to experiment with functions, and that's the best way to learn. And it's a really useful technique to understand topics like domain, the inverse function, and how to use composite functions. You could even try composite of 3 or more functions like f, g, and h. See if you can come up with what's the single function to replace this, right? But it'll still be the same concept that you would use to extend your knowledge. Now, that's one of the areas I feel like students lack these days, because once they learn a technique to solve this f and g, it's almost like they've memorized things. And so once you get a situation where you have 3 functions, they completely blank out. They have no idea as to what to do. But if you really understand what we are doing by composing and understand the net effect, then you have a better chance of problem solving. So that's a real what I wanted to push through in this video, using analogies and illustrations. So hopefully you've got to know more about functions, the underlying principles of functions and inverses, than what you had at the beginning of the video. So that actually we can wrap up here. I'll see you in another video.